So in a previous video, I talked about freezing point depression and the idea that if you take a solid solute and dissolve it in a liquid solvent, you will decrease the temperature at which it freezes. And we went through the explanation as to why that occurs. Now, what happens when you take the same solid solute in the same solvent? What happens to the boiling point? Remember, the boiling point is the temperature at which the vapor pressure of the liquid equals the vapor pressure of the atmospheric pressure. So what do we expect to happen? Well, it's a bit of a different explanation than what happens to the freezing point. See, the freezing point went down, the boiling point's actually going to go up. So what's going on here? Well, think back to the boiling point. We can increase boiling point by increasing intermolecular forces. This is effectively what's happening when we add a solid solute. The liquid is actually more attracted to the solute than it is to itself. And so the boiling point is going to increase because you have the solute molecules holding onto the solvent stronger, which is raising the temperature at which it needs to boil. So what is the actual quantitative relationship between boiling point changes and the amount of solute added? Well, it's going to look really similar to freezing point. And again, it's because we're going to make two major assumptions. We're going to assume we're sufficiently dilute, and we're also going to assume that this is a colligative property. It doesn't matter what's dissolved in the solution. What we get is delta T equals KB times I times N. Now, this looks just like the freezing point formula because it is the freezing point formula just with a different variable for that proportionality constant. Now, your delta T here is the boiling point change. And we will always add this delta T to whatever the solvent is. So in the case of water, if we want to figure out the new boiling point, it's 100 degrees plus this delta T. Your KB is still solvent specific. So this is going to be true for water, it's going to be true for acetone or ethanol. It doesn't matter what's dissolved in there. But it numerically is going to be different than KF. So if you use KF and KB interchangeably, you're going to get the wrong answers. This is going to reflect the effect of intermolecular forces changes within the liquid. And again, it's very solvent specific. Your I is once again your Van Hoff factor. And it's going to describe how many things your solute breaks into, because the more it breaks into, the more can it mess with the intermolecular forces between the water molecules. And your M, once again, is your molality. So here's how you calculate a boiling point change. And again, the boiling point change is always going to increase because the solvent is always more attracted to the solute than it is to itself for a solid dissolved in the liquid.